Oh, he's also giving me the option of leaving if I don't want to be recorded. Okay. Okay. So yes, good morning, good afternoon, wherever you are. So today we welcome Mehmet Dogar, who is an associate professor in the School of Computing at the University of Leeds, right? And we are very happy to have him here. He's going to talk about his research, which typically focuses on robotic object manipulation. And he leads a group of researchers there in this topic at University of Leeds. He's also the co-chair of the IEEE RAS Technical Committee on Mobile Manipulation, and he's also an associate editor for IEEE RAL, Robotics and Automation Letters. He was a postdoctoral researcher in CSAIL, that is in MIT in the US. I believe he got his PhD from Carnegie Mellon Robotics Institute. And if I remember correctly, he did his undergraduate stuff at METU, right? Middle Eastern Technical University, yes. Because I happen to have read some of his early papers there. So, we welcome him here. It's very nice of him to come give a talk. So to you then, Mehmet, go ahead.
Thank you very much, Mohan, and thank you all for coming to the talk and organizing this. I will give a overview of the different work we are doing in the space of object manipulation. And most of my talk will focus on physics-based object manipulation, though at the end I will also touch a bit on work we do in human-robot collaboration and collaborative manipulation as well. So the type of tasks that I am very interested in are these physics-based interaction tasks. And here is an example. Here there's a robot. Can you see my pointer? You can see my pointer. Is that right?
Yes, Mehmet. Yes,
okay, can. Good. Yeah. And the task is here to reach for that object with the green tape on it, and for that it needs to push on these obstacles. You know, there's a virtual barrier on top, so it can't go from the top. It needs to push on these obstacles. When these obstacles are pushed on, they will interact with each other, obviously. So it needs to be able to predict how that interaction will continue, and it needs to make sure that the target object gets into the hand before other objects. It needs to make sure things don't fall off the edge of the table, and needs to be able to predict the physics of this interaction and generate actions that will reach the goal. So this is the kind of tasks that we are interested in. And other aspects of, for example, physics-based manipulation, where physics models play a big role. We are interested in the accuracy of the physics models that you actually need. So to give an example, if you have a task where the task is to push this object into this large green region on a kind of a large table, well, we think the robot can be fast, and even if it has uncertainty about its actions, it can still do that. For example, one controller should be able to adapt to tasks like this, but also to the same controller then should be able to adapt to tasks like this, where you take the same thing. It is a very similar task, but now the constraints are much more higher, in the sense that the target region is much smaller. The strip that the robot needs to push the object is much narrower, and then the robot needs much more accuracy and a much higher certainty in its actions, and then the robot naturally slows down and tries to make sure its actions will move the object where it wants it to move. So and we are interested in physics models being more or less accurate and being able to use these in a task adaptive fashion like that. So in general, that is the this is just to give you examples of problems that we are interested in. But taking a step back at the higher level, why are we interested in these tasks? Because our human environments are cluttered environments where just detecting one object and reaching for it may not work. The robot may need to push on things, topple things. So a real physics-based interaction is needed, and not only in human home environments, but as some of you might know, there has been this Amazon picking challenge, and in a real Amazon or in any other warehouse where someone needs to reach into bins like this, where there are multiple objects, and you need to push these to the side and reach for an object and get it into the box, and there again maybe nudge other objects to squeeze that one in. So these are all examples of physics-based interactions where predictions about how objects will move when the robots or other objects make contact with each other is important. And the problem is how to plan and control robot actions to perform such tasks. That is why we're interested in it. And again, on the more this is the application side, but on the more science side, what we are interested in is and what I have been interested in for the last 10 years is going beyond geometric motion planning. So motion planning has mostly focused on this idea of collision-free robot motion, where you are given a start position and a goal position and a geometric model of an obstacle and a robot. And then the problem has been generating this motion to avoid contact. And we have made great progress along this, but the question is, how can we generalize from that to move beyond geometric models of the environment to physics-based models of the environment, where then the robot can search for actual physical interactions that will reach the goal. Of course, this increases the dimensionality, this increases the uncertainty. So there's a lot of problems that comes with that, but that is where I am interested in going. So that is my high-level vision in my research. So so this is what I mean by physics-based manipulation planning. Now, we have been doing some work at Leeds over the last 5 years since I've been at Leeds, and I will mainly talk about those. But first, I want to take a step back and give a brief overview of my work since my PhD and postdoc to basically motivate what I have been doing then at Leeds. So I will first start with, and I can divide these phases into two easily, actually, because before coming to Leeds, I have been mostly working on generating open loop physics-based plans. Okay, so until I start talking about closed loop, basically everything I present will be about planning open loop actions. When I say open loop actions, the robot looks at a scene, creates a sequence of controls, actions, and just closes its eyes and executes it. And that has been the question: how can I generate such open loop plans? Has been the question that I looked at back then. And this was motivated by, back then I was working on this robot, which would use its sensors to detect an object, and it would do regular, grasp planning and motion planning. It would plan a grasp, move its arm there, close its fingers, and it would grasp the object. And this kind of an approach was based on this traditional motion planning and grasp planning. Basically, there's the grasp planning approach where you search for force closure grasps on an object. So you given a hand model, you look at where your fingers make contact with the object, and you can look at the frictional interaction at those contact points between the robot hand and the object model. And then you can analyze that situation to see if that hand pose, when the fingers clamp on the object, will give you a good firm grasp. And then, given an actual scene like this, and given a hand model, you can search for different positions for the hand to be, and look at where the fingers will lay on in terms of the contacts on the object, and then you analyze that. And then once you find such a good hand pose, what has been traditionally done is you would do a motion plan, right? So wherever your arm and hand currently is, you would then do a collision-free motion plan to move the hand to that planned hand pose and then you close your fingers. So that has been the approach, and that has been the system that we have been using on this robot. But while it was successful at certain times, it would not work at other times. So here again, the camera detects the object, the hand moves there, and it fails. And the reason why it fails was uncertainty. Okay, so the camera tells us the object is here, but actually the object may be a bit off, or maybe it's here, or maybe it's here. So these are all possible poses for that object. And the way I became interested in physics-based interaction was actually initially because of this uncertainty. So back then I was taking a class from Matt Mason. Some of you who work in object manipulation may know, who has been interested in pushing, and he has used pushing actions to reduce uncertainty. And I was interested in basically using some of those methods in a case with a hand like we have on this robot, and planning actions such that when we have a grasping task, we can use pushing to guarantee that all those different hypothetical poses of the object would funnel into the hand. And so that even if we are uncertain about the object's pose, we can still grasp it. Okay. And basically, in my PhD work, I analyzed the interaction between the hand and objects and came up with what are called capture regions. So this black curve here is a capture region of a certain pushing and grasping action. That's pushing and then closing your fingers. And so that, and this is for a circularly symmetric object, but if the object is not circularly symmetric, these capture regions would have 3 dimensions, where the vertical dimension is the rotation of the object. But basically, this was to reduce the uncertainty, to deal with the uncertainty about the pose of the object. And while that was my initial plan, then one thing that I realized was also that this was useful. This pushing action was also useful in grasping objects in cluttered scenes. So like this one, where the robot was able to, in addition to reducing uncertainty, the robot was able to, for example, if the goal here is to grasp this box, while it may not be able to put its fingers here and here on the side of this box to grasp it in its original position, it was able to come up with these pushing actions to also move them such that they were graspable, right? So then we started thinking about, oh, okay, so this pushing thing is not only useful for reducing uncertainty, but also for grasping objects in clutter, because you can move objects away from clutter where you can then grasp them. Which was interesting, because that was also something not possible when you take only the geometric motion planning approach, where you only have a geometric model and you assume that you have to grasp the object on the table wherever it is at that moment. Then we extended that work, and we said, okay, if we are able to push the object we want to grasp, why don't we also think of pushing other objects, possibly obstacles, because obstacles may be moving out of the way, right? So, and then I worked a bit on these motion planners that can make contact not only with the object to grasp, but other movable objects in the scene. But again, here, remember that, I am using open loop paradigm still. So this planner was looking at how the objects were predicted to move according to a physics model. And it was generating that whole plan and then just executing it. Okay, so it is, once it generates a plan, it closes its eyes and executes it. As I just want to emphasize that this is all still open loop, but it was able to generate grasps like this, for example, where our goal is to grasp this can at the back, and all those arrows are different ways to approach that can. But the robot is able to predict how these other obstacles will move and pushes this particular way to approach it, which does push the obstacles away and then reaches for that can. Okay, so now, though, like one problem that we had in that previous method was that since we are using the open loop approach, and I think this is an important point that I want to get across. So since we were using the open loop approach, we really needed to have a small degree of uncertainty on the object's motion. What I mean by that is, if our predictions about how objects, the obstacles will move were very off or very inaccurate, then the plans would fail. And to guarantee that, in the previous work that I just showed a video of, we would only plan actions where once we contact an object and push it, that object wouldn't contact any other object. So what I mean by that is, while the robot was allowed to contact multiple objects, so multiple robot object contacts were allowed, no object-to-object contact and pushing was allowed in the previous work. So we didn't want any object pushing another object. The reason was that because the uncertainty in that case was exploding and our planner was often failing under those, and we were able to keep the uncertainty to a degree where we can still execute open loop plans only if objects were only pushed by the robot and objects wouldn't push other objects. Okay, but of course that that means relatively sparse environments. And if we look at this image, of a real fridge, if you start pushing something here, it will go and touch another object and it will start pushing that. So in more realistic settings, that kind of an open loop approach was not working great. And therefore, when I moved to Leeds, one of the things that I wanted to do was to look at scenes like this, which I shown an example at the beginning, where when you start pushing on objects, they actually go and contact other objects as well. Multiple things push on each other. And to deal with this, we wanted to take a more closed loop approach of dealing with the problem. Because in this setting where you have, if you just do an open loop execution, this is just an example. If you just make an open loop plan and execute, here what we are showing is in simulation, in your physics model, it thinks that it will grasp the green object, but actually if you just execute it in real life, such multi-object interactions most often do not move according to your predictions, and then you can end up with failures. So that was the reason why we had to move towards a more closed loop approach. Okay, so this brings me to then our time at Leeds, and where we took the approach of online replanning or model predictive control, where I'm checking how I'm doing with time. Okay, so here basically we make a plan, and then after we make a plan, here this yellow arrow, let's say, represents the plan that the robot generates to reach for the green object. What we do is we only execute it for a short duration, the initial part of the plan, and then we look at the environment again. We perceive the environment again, and we update our model of the environments according to how objects moved, which is something that we didn't do in the open loop case, right? And then if things are going according to the plan, according to how we thought the objects would move, then we actually keep executing the plan. But otherwise, we would run a replanning cycle. So if objects move differently than we predicted, then we would replan. And when we replan, of course, in model predictive control, one thing that you can do is what is called warm starting. That is, you don't have to throw away this remaining portion of the plan, but you can actually use that to initialize your next planning cycle with the hope that it will help you find a new plan faster than starting from scratch. By the way, if there are any questions, please let me know. And unless I don't know if I can see you when you raise hands, but please feel free to speak up as well.
1 minute. If that's the case, then if you raise hands, either Martin or I can spot it, or you can say something in the chat and we can call on you. Okay, so Mehmet can go on and we can take charge of interrupting. Go ahead, Mehmet. Yeah.
Thank you, Man. So, we then frame this problem as a trajectory optimization problem, where you start with an initial trajectory. So, for example, a straight line trajectory. And then you take that, this is a sequence of controls and states, and then you optimize that according to some costs. And we devise some costs according to where the target object is, and the terminal state of the final position of the hand with respect to the target when you execute that trajectory. We also added some costs according to how close an object is to the edge of the table to keep objects away from the edges. So as objects got closer to the edges, we impose some penalties on the cost. And that's an optimization problem where the constraints are coming from the physics model. So here F is the physics model that maps the current state and controls to the next state, right? And we used we used a sampling-based trajectory optimization method. So if for those of you who are aware of STOMP, we basically used a version, like we modified STOMP a bit to apply to this problem, and then we used that to solve these problems. And then we were able to generate more closed loop actions where we were able to actually push on multiple objects that would interact with each other, and we were able to generate these actions. But there were still some limitations. Okay, what are the limitations? So first of all, this was slow. The videos that were playing at 3 times speed, but actually, I will talk about a few different limitations here, and resolving those limitations do require us to do even more simulations in these planning cycles, and then if you were to do that, it would become even more slower, right? So that was a problem, and speed is particularly problematic for this kind of online replanning, closed loop execution, because it means you are if you spend seconds to generate a new plan, then you're stopping in between execution and generating the next sequence of actions. And this slowness was particularly due to the fact that physics-based predictions running a simulator is slow, and I will get to that. But that was one of the big limitations of this method. The second is that we are using optimization methods, and the planning problem then had to be locally solvable. Okay. And otherwise, this planner could get stuck at local minima, and that is another problem of these kind of planners. Another issue was that we were assuming full observability, right? So if I go back to, you might have been wondering, what these little balls on these objects are. I'm sure some of you know what they are, but for those of you who don't, they are markers that they are infrared reflective markers, and we have infrared cameras all around this scene to detect each object's position at each time step. Okay. So we know their position with high accuracy at each time step. And not only that, but if you're reaching into a, so let me then go there. If you're reaching into a fridge like that, there are actually objects that you don't even see at all, right? So for example, this object behind here, and there might very well be something else behind this one. So you don't actually have information about all the objects in the scene. So that is a big assumption, having full observability. So that was a limitation of what we had there. Another problem of this, another limitation of this approach is that the control problem here has to be intrinsically stable. What I mean by that is, if we have one bad contact mode, then it shouldn't lead to a catastrophic failure. And this is not true all the time. So in that sense, the task that I have been showing, pushing these objects on the table, is easier than some other tasks where if you're manipulating something in the air, for example, if you make a bad contact, a bad move, and one bad mistake, and the object may just fall to the ground, right? So this is a more forgiving task in that sense, and we need that forgiveness for this approach to work, really. And finally, you have what I have been showing is this open table with no edges or anything, which is because actually when there are static obstacles, they can be problematic, particularly when objects are jammed. When you're pushing an object against the edge of a table, then it can be difficult to deal with because our physics models are much more uncertain under these cases, and it is much more unstable, basically. I mean, we are able to run our planners in these cases as well, and sometimes they do work. So here is an example. This video is not sped up, so it takes, and you can see how slow it is, which is also good. But so we are able to, for example, in these simple cases, as you can see, this object is pushed against the edge. Even the gold object will kind of be pushed up against the edge. But so we can deal with these cases sometimes when it is easy, but not robustly enough. So basically, that is another limitation of this system. So in terms of these limitations, of course, we want to be able to work on all of them, but what we have been able to not address in terms of just completely solving them, but in terms of investigating them, has been this three. So while the others are also very, very important, I will mostly focus on this three in the rest of this talk. Because we scratch the surface on those ones, and particularly so I will now go over the different chunks of work we did about these. So in terms of the slowness of the approach, one work we did has been using learning to reduce the planning horizon. Okay, and I will talk about that. If that raises question marks about what that means, I will get to it. But that is basically the idea of not planning until the very end, but until a few steps into the future only, so that we can be faster in generating plans. And we have then also used this similar learning approach to address full observability assumption, such that we can learn to predict unseen object poses in that cluttered environment. So that not completely, but partially addresses this problem. I will very briefly talk about that. In terms of addressing the slowness problem, we also looked at using computationally cheaper physics models and what that means for planners and the different kind of tasks we can do. And I will talk about that. And in terms of the planning problem being solvable only if there's a local solution to it, starting from our initial trajectory, right? I said we have to initialize this trajectory optimizer with some initial trajectory. And if and it can find a solution only if there is a solution in the basin of attraction of that where we start with the initial trajectory from. One approach that we looked at has been using human intelligence to get high-level plans and doing the low-level optimization autonomously, but getting human input at the high level to see if we can get like escape out of local minima and get to places where we can then solve the problem. So I will then now reorder these 4 points like that. So these are those 4 points and go over them one by one. And the first one will be to use learning to reduce the planning horizon. And this has been mainly driven by my PhD student, Wissam Benjani. I should not have said my, actually, because we co-advised Wissam together with Matteo Leonetti, who's also a lecturer in the school, who does mainly reinforcement learning for robotics. And Wissam defended his thesis just last week, and passed. It is great to talk about his work just now. But Wissam's idea was that, we don't need to plan until the goal, right? In the example I have shown, the robot plans until it gets the green object into the hand. And as it executes, every time it needs to replan, it still plans until it gets the green object into the hand. What we were saying was, to make things faster, to make planning faster, let's plan only a few steps into the future. But then the question is, how can we know this resulting state is a good state, right? So that is the problem. And that is where you use heuristics, right? And then the question was, like, can we learn heuristics? And Wissam was interested in using, like, integrating the policy learning and deep learning approaches with learning a good heuristic, but using still model-based planning approaches and combining the powers of two together. So basically, what he did was, so given a scene like that, he was interested in mapping the state to a physics simulator, okay, so that we can run a model-based planner. So this state may be represented as this in the simulator, let's say. And if you were wondering about how this exactly happens, so basically we were getting the real world data, so a camera image of the scene, and we are running it from some computer vision modules that were mostly off the shelf for us, that would give us relative shapes of these different shapes of these objects, and the location of the goal position and the robot hand. And then we would initialize these in a physics simulator based on the output of those vision systems, okay? So this representation here is that. So this is not only an image, this is also a simulator representation of the real scene, okay? And then we run our model-based optimization or planning algorithms in this simulator, but not until the end, until we get the goal. But what we do is we run it only for a few steps, which is a parameter of this framework that you can adjust. So we run only until a certain depth, so which is what I illustrate here. So so here the depth is until, like, depth of 3, right? So only for 3 actions into the future, 3 controls into the future. And then the question is, which one of these is good? And what we do is, for all these resulting leaf nodes in this search, we want to know how good that is, so that we can then backpropagate all those values and then pick the action that is the most promising. And for that, we were using to evaluate all those leaf nodes. We have been using a learned heuristic in the image space. And this is in the image space of the simulator, and so that we can really train this in the simulator, right? So, and this is a little bit radical in the sense that what most people try to do is train these deep learning systems in the simulator such that they will then work in the real world by adding noise or creating lots of variance in the simulator. What we have been interested in doing is mapping the real world to the simulator even during execution, so that our learning can stay in the simulator space, but then we put the burden on the vision system to map the current real world to the simulator accurately. But in terms of training the heuristic, we would just then generate offline, right? This is not online, offline. We would generate lots of demonstrations in the simulator. We would create plans, and using those plans, we would do some imitation learning, and then we would do reinforcement learning on top of that, again, still in simulator. And then that would give us a heuristic about how good certain states in the simulator are. And then we would be able to use those heuristics in our search until a short horizon, right? So, and again, the important thing here is that the heuristic and the planning, everything stays in the simulator space in this. And then we were, so here, let me explain. So this is the real world, and then a computer vision system is again working on this and mapping it to this simulator. And this is both the simulator, and you will see this kind of moving, that is the simulated actions evaluated in this physics simulator until a few steps into the future. But it is also, this is also what is being fed into the neural network to then predict how good a resulting future state is as a consequence of the action. Okay, so what you see here is all those evaluations of different actions, but at each point, this is being mapped to the simulator and then searched. Okay, so now there, of course, like so this was able to make things a bit faster, but there are many limitations. So this was only in the 2D space that we were able to get this to work, and how to do all this in 3D is also still not something that is very clear, and we weren't able to, like, we didn't spend too much time on it yet, but like it is not obvious to us. And also this was still working in relatively familiar scenes. So due to the learning approach, if the a scene that the robot is shown is quite different from, in terms of the objects or in terms of the organization of the objects with respect to each other, is very different from the training data, or if there are, if this is a real shelf with obstacles like edges on the side, then this whole thing kind of fails and you have to retrain it from the beginning. So there are, again, some limitations to this, but we were able to make things a bit faster by using this approach. Now, one other thing that Wissam used this approach to do was to learning.
Sorry, Mehmet.
Yes.
Maybe I can interrupt you at
Yes.
this stage, because there have been, in fact, a couple of questions in the chat. Do you want to answer them now, or do you rather?
Why don't I hear them? And if I think they're longish discussions, I can say let's discuss it at the end. If they're quick answers, I can answer them. Is that fine?
Yeah, sure. Yeah. So the first question was which sort of semantic descriptions are actually used for the objects?
Shall I state the question? Hi.
Hello.
Thanks very much for this. I suspect I know the answer, but I've been wondering whether your system works out 3D locations of objects and then derives their relationships, like gaps between them and so on, or whether it can directly perceive relationships, gap sizes, and so on, and only look at the relationships that it needs for a particular action, which is what I suspect the humans would do.
So maybe my use of semantic was confusing there, because we don't explicitly extract concepts like gaps between the objects or relations between the objects. What we really extract is the object's shapes, and we recreate objects with that shape in the simulator. The reason why we were using semantic in this setting was only because we also have, so one problem with deep learning, like reinforcement learning based, deep RL based approaches, is that you can't really, apologies, you can't really train them, you can't really use them for the object that you want when you test them. What I mean by that is you can train your system to push a red object to the goal location, and you train it to push the red object to the goal location. And when you execute things, you need to get it to push the red object to the goal location. To get it to push the blue object to the goal location, it is not perfectly clear how you would do that. Now, what we were doing here, the reason I was using semantic is that what we are doing here is we are also detecting the goal location and then the hand, for example, and then the target. So here the task is to push the apple to the goal location, and we were color coding them. So when we map this to this simulator, we also color code them. So if the task is to push the green apple, the apple, it becomes a certain color of green, and the goal location becomes a certain color, and the robot becomes a certain color, and all the obstacle objects become a certain color. So that was the kind of semantic information that we were using here.
Okay, I think you've answered my question. You're not actually perceiving things like changing gap sizes and changing directions between surfaces and so on, which is what I think evolution produced in animals.
Okay.
Okay, I think there's one short second question.
Yeah.
Do we assume the robot hand cannot adjust the angle to fetch the object, for example, from the top, because it always goes from the side in the videos? Like on a horizontal approach?
It can. There's no limitation in that sense. I don't know if the particular video. So like from the side like that.
It's like the orientation is basically always the same. It just changes the angle.
So you mean it is flat to the table?
Yes, exactly.
Okay. Yes. It is limited. Yes, in that sense that this is a 2D planner. And when I say 2D, the hand is restricted in that sense. That's correct.
Okay, thank you. I think then we should move on.
Okay,
thanks.
Cool. So I just, in terms of this, I just wanted to show that this wisdom as the final step, he also extended this to the case where we are now looking at, okay, let me see. Okay, so we are not now looking from the top down. Okay, so now the camera is on top of the robot hand. To address this issue of full observability, right? So now we don't see all the objects, and we still use the same kind of representation, but this representation now also includes the shadows, which you can see as these gray areas here. Okay. And so this is, you can see that this is still created, the simulator image is still created from the top down, but it doesn't matter. Like, we basically, what we have is in the real world, we have this camera on the robot hand that perceives these objects, and this is then instantiated in the simulator, and then this image is rendered in the simulator, and this is what goes into the neural network, okay? And this is where the model-based planning also takes place. What we tried as well was to then also train the same neural network, which would share the network. So the network would have not only the policy head, which would suggest the actions to execute, and the value head, which would suggest the values of certain states, but it would also have a prediction head, which would predict the target object location. Okay, and again, this would also be trained, obviously. So here, for example, you will see green object appearing in different places. Those are all possible places that have been predicted by the network. Okay, and based on those predictions, the simulator is the planner is trying to identify the object. And you know, if I go back, so the object is actually behind this one, and you know, the system will be predicting it in different places and coming up with actions, and it is basically choosing the actions that that according to those predictions of the hidden object, where which actions give the most expected reward of finding the hidden object and grasping, and this is the hidden object here, and then it goes and finds then and extracts it. And again, you know, we can initialize this with different objects to search for, and it hypothesizes these locations and then search for them. So that was one extension. You know, this doesn't address the full observability assumption fully, because you know, this only reasons about the hidden object. You know, but you can see we still have these tags on the object, so we still have certainty about the object's positions if we see them. Which you normally won't have if you were doing more realistic computer vision or perception. But you know, this was one step in that direction. Okay, so I'm running short on time, which was what I expected. But so I want to talk a bit about other approaches we took to make these planners faster. And one of them was looking at using computationally cheaper physics models. Okay, so when we make plans, we have been using these physics simulators, right? I'm sure some of you have been using, for example, you know, Mujako, or some of you use PyBullet, and you know, there are many other simulators out there. But the speed of these simulators are still at the level of real time. What I mean by that is to simulate 1 second of interaction. You know, if you want to simulate moving your hand forward 1 second with a relatively a realistic scene where you have a few different objects, you need to usually simulate around 1 second. So you know, you need 1 second computer time, right? So that is what I meant by real time. So to query the simulator about what the consequence of executing a 1 second action, what you need to do is to run the simulator for 1 second. So this is really bad, because you know, usually our planning algorithms, control algorithms, need to query the physics simulator, the predictor, thousands. Actually, it would be good if we could query them millions of times. Then we could also be able to deal with uncertainty. But like, you know, we need to query these simulators thousands or millions of times to execute 1 second action. But actually, you know, only querying them one time is all that we have, all the resource we have. So it is really important that then we are able to query physics in a much faster way. And it doesn't, and the idea here was that it doesn't always have to be that our physics models are very accurate. Our physics models can be computationally cheaper and coarse, right? So by coarse physics models, what we mean are inaccurate but computationally cheap models. And then by fine models, we can talk about these simulators, which are more accurate, but they're computationally really expensive. And so Wisdom Agbo is this PhD student who has been working on this. has been interested in using two different type of models in planning and control. And again, so if you taking a very simple problem, if you want to predict how this box will move when you push it with a cylinder like this, what you need during planning and control is usually to predict a sequence of states of how this box will move. And just to illustrate it, this is basically an initial value problem, right? You are doing numerical integration forward in time, something like Euler integration or Runge-Kutta integration, and that gives you how the box will be moving. So this is this vertical axis is time here, let's say, and this is the state of your system. Now, and this is this is sorry. This is how your box moves, okay? So this is how your box, let's say, realistically moves when you do the fine integration, when you really take the simulator and do the forward integration. One thing that Wisdom has been interested in was using instead of coarse models. So by coarse models, this is just an illustration. Please don't take this too literally. Here it's a constant function. A coarse model doesn't have to be a constant function like it is shown here. And one problem with this illustration, and I apologize about it, is that the coarse model here magically ends up at the same point with the fine model. This is not necessary. We should create a new version of this illustration, okay? So the coarse model should end up somewhere different because it's coarse, it's inaccurate, okay? But the important thing here is that the coarse model is a simple prediction, and it is computationally cheaper to run. So, for example, here is the actual model that Wisdom used for this pushing task of the object. And he's not running a physics simulator here. What he's doing is moving the box. As long as there's contact between the box and the cylinder, he moves the box with the same translation of this pusher. And depending on the distance of the pusher to the center of mass of the box, also applies some rotation. Okay, so he has a simple rule. Instead of running the physics simulator, he just applies the simple rule. And of course, it is super fast to apply the simple rule to the box. So generating the coarse prediction is quite fast. And it is about 100 times faster, or maybe even for this model, maybe it is even more faster than integrating with the simulator. Okay. Now, what we do is we use something called parallel in time integration, which is a method that exists. We collaborated for this with some applied mathematicians that work on parallelized solutions to initial value problems. Basically, what they do is if you have a coarse model and a fine model, what you can do is you can use parallelization. First, you run your coarse model on in series, so on the same core, let's say, and you get all these initial points for different segments. Let's say you divide your time into 4 segments for this illustration. And what you do is you only run the fine model in parallel for these segments independently, starting from the predicted initial positions of the coarse model. Okay, so what you do is you run the fine model only for 1/4 of the time. Okay, not for the full duration. And this is one iteration of this algorithm. If you are not happy, that what you do is you can then propagate. I won't go into the details, but there is a way to then propagate the predictions of the fine model using the coarse model again. Okay, so you do a serial pass over all the time duration again. That gives you an improved prediction. But you have still only ran your fine model only 1/4 of the time. Okay, and if you're not happy with this, you can then take these predictions, these points, and then run another iteration where you do another fine prediction, and that means now you have run your fine prediction over 2 time steps, right? But your predictions will get better, And if you're still not happy, then you can run this for one more iteration. And if you run this for even one more iteration, then there is no point in running this algorithm because you have already run your fine model for the full 4 times that. And you could have as well run your fine model from start to end. So what you end up with is, so here this 0 to 4 now represent the number of iterations you run this algorithm. And this here shows the error, all right, the root mean square error in log scale of the prediction of where the object ends up when compared to the fine model prediction. And with each iteration of your algorithm, you get errors that drop down quite quickly, and you drop to 0 at 4 iterations because, again, it is equivalent to running the full fine model. Okay. So, but the thing is, actually, we have now this spectrum of different models we can use, right? Starting from the very coarse model to the running the simulator for the full duration, we have a spectrum of models with different accuracy, but also different computational expense, which we can choose. For example, like, there is this great work from Alberto Rodriguez group at MIT, where they basically just apply the same pushing action in real world on the same object, and show that there's actually stochasticity, there's error in there. So even when you use even when you do this in the real world, there's stochasticity. So we don't, some of the accuracy here we get from the simulator is useless accuracy. We are just overfitting to the simulator, right? We don't need that. So actually, you can make do with running these simulators at a much less accuracy. And if the task requires less accuracy, you can even just make do with the coarse model as well sometimes. So basically, he used this scheme to show that we can do much faster planning compared to running the fine simulator. We have been investigating these approaches to generating these actions. But he has also used this same approach to then adapt the physics models to the task for the examples I have given at the beginning of the talk, to basically decide on what kind of accuracy we need from the physics model, depending on the task. For example, for this task, you may need only a very coarse model, so you can be very fast, but this task, you may need very accurate predictions, so you may need to be slower. But the same controller basically adapts to the task. Okay, so I think I am now at the 1 hour mark since I started, right? So I will, I mean, I know that we had 1.5 hours for including the discussion. So, but I have more slides. So what I will do is I will be a bit faster for the remaining. But if you want to hear more details about what I will show after this point, let's leave it for the discussion, and I'm happy to go into the details. But I will skip some slides after this point so that I can be a bit faster. And the last point that I want to in this context talk about was the human in the loop planning, and this is what Rafael Papallas and other of my students have been working on, which was to deal with the problem of local getting stuck at local optimas, local minimas, right? And Rafael's idea was that humans are good and quick at making high-level suggestions, and whether we can actually integrate such suggestions with local trajectory optimization. So, for example, in a scene like this, again, if the robot wants to reach for the green object, and when you run the optimizer, it gets stuck. It says, I can't find a good solution for this one. What happens is that it goes back to a human, and the human can suggest to move this object here. So the arrow represents the human input. The human says, push this object in this direction. And this then gets integrated into the trajectory optimization, okay, in 2 ways. One, it changes the initial trajectory. So the optimizer, remember, This optimization we always initialize, and we have been initializing it with a straight line or some other way of autonomous initialization, but we use the human input to then change the initial trajectory so that we start from a different point for the optimization. But also it gets integrated into the objective cost term so that the robot, in addition to getting the object into the hand and not dropping objects off the shelf, which are part of the cost term that it optimizes for, after it gets a human suggestion, it also makes the suggestion part of the objective term so that it is also trying to push this object close to the point that is indicated by the human, and with the hope that it will actually help it escape from the local minimas and find the solutions. Okay, so the human suggestions are integrated into the trajectory optimization as part of the initial trajectory and as the cost term. Okay. Now, one thing we wanted to do, of course, was we assume that there's a human who will help us, and we don't want to spend too much of the time of the human, so we want to minimize the human time spent. So Raphael implemented things such that the human input is requested only if the optimization is stuck at a local minima. Okay, so if the robot is able to solve the problem by itself, it does. If it detects that it's stuck at a local minima, it gets the human input and then it updates its optimization problem with that, and then it continues the optimization. And the nice thing about this was, we tried to do this in a multi-robot scenario. So, the scenario we had was, your robot is in a warehouse, and there are lots of robots like this that needs to reach for an object, and maybe there is one human operator. Okay, so. And here, we show all the robots at once, but you can also think of these being behind the scenes. I mean, we wanted to show them here because we wanted to make the point that there are multiple robots there. But in a real warehouse, you don't need to show the autonomous robots to the user. You only need to show the robots that ask for help. And here, what you will see is that these robots are moving autonomously, and one of them decides that it is at a local minimum, so it asks for human help, and the human gives some help. As you will see the pointer of the human, and the white arrow indicates the human help, and that completes the task. And then this one says, oh, I need help as well, and some of the other ones actually work by themselves and then complete the task autonomously if they can. So this is an approach where one human, we were looking at whether one human can actually control multiple robots simultaneously by high-level input. Okay, so here is, for example, that case where the human provides some help, and then the robot uses the human help to adjust the initial trajectory, and then which helps it actually solve the problem. Okay. So this was basically what I wanted to talk about physics-based manipulation planning, and this has been my focus. But as I mentioned at the beginning, let me just very briefly mention that we are also interested in collaborative manipulation planning. I did some work back in the day during my postdoc where I worked on multiple robots, planning grasps on things and doing motion planning with them. And once I moved to Leeds, I was interested in doing this in a human-robot collaboration setting, and we are particularly interested in forceful collaboration. So if you have a board like this, if the task is the human wants to cut a circle, how can a robot hold the board for the human such that it will resist these forces, it will rotate the board to make it comfortable for the human, and complete these tasks collaboratively. Okay, so I had a postdoc, Luis Figueiredo, who finished his postdoc now and moved to Munich now, Technical University of Munich. And Lipeng was my PhD student who also finished at Tencent Robotics in China now. But so, this is about planning grasps that will resist the forces that will be applied. So, if the forces here when the human is cutting are pointing upwards, the robot should pick the correct grasps. And as the human moves along the circle, the forces will change. that the human applies, and the robot grasp should change. That is part of the planning problem, because otherwise there may be failures. But then there's also part of the problem how to regrasp the object, because the robot needs to change its grasp on the object as this interaction continues. So I won't go into details, but Lipeng and Louise implemented a planner that can make choices about grasps on the object. These red things here are the gripper of the robot, a sequence of grasps, which then needs to be connected with the regrasping actions and then continuous motion plans at the lowest level to make sure that the board can be firmly held against all the forces that the human will be applying during the interaction. And people usually ask me, like, is the task given? Yes, we assume that the task, the sequence of forces that the human will apply, like the circle here, is given. Okay, so it is one assumption in this model. I will skip that. But one thing that the final thing I want to say is that one thing that we also looked at in this context was optimizing how to hold the board for human comfort, predicting what kind of muscular efforts and joint efforts the human will need to apply. Because if I wanted to hold something for you, I can hold it like this, I can hold it like that, I can hold it like that, and some of them will be more comfortable and less comfortable for you to do that. And we have actually done some experiments using EMG sensors and motion capture sensors to measure the muscle effort of people when they do such tasks. And we have been implementing planners that try to minimize the muscular effort. So here, for example, this is user defined. So here the human chooses the pose. These are two different tasks. One is they puncture a hole. One, they cut along a line. This is when the human chooses the positions. This is random positions. And this is our planned positions according to our model of the human musculoskeletal structure. Okay. And we would measure using EMG readings what the actual muscle efforts are in these different cases. And we worked with some biomedical engineers for this to help us with those muscular modeling and measurements. And these are some results. So for example, for cutting, it wasn't great. So we weren't able to really make any distinction between our planner, which is shown by the blue region here, or the user defined. Even the random was quite scattered. So for a cutting action, which was longer, it wasn't clear. But for the drilling, like in a puncturing action, where you just push for a short duration, we were actually able to see a statistically significant difference between our model and the other models. Here, on the vertical axis in both plots, we have muscle activity, and in the horizontal axis we have muscle activity, and the vertical axis we have the generated force. And we want things to be at the lower left corner. That is less effort by the human. And the blue region represents our planner here. And then for simple tasks, we were able to observe that we were generating less muscle effort on the part of the human. And this is something that we are continuing to do. Particularly, this is right now only looking at this is analyzing the problem as a static interaction. So this is analyzing the human only at a given configuration, not over continuous motions. And something we want to do is to extend this to continuous motion so that we can have more smooth interaction with the human. All right, I hope this final part that I was fast with wasn't too confusing. If you have questions, I'm happy to reply. Thank you.
Okay, thank you, Mehmet. So I'm on speaker, right? So yeah.
Thank you. Yeah.
Okay, so now questions. If anyone has questions, you can use the raise hand feature, or you can click on yes, or you can leave a message in the chat window. Where shall I pick this up from? I think we asked questions that Aaron had, right?
Yes.
And should I then? Okay, Xiao Wang. I mean, you had a question. Do you want to speak up, please, or is it already answered?
Yeah, I've got answer. I think he answered already. Thank you.
Okay, good. Then Jin, you want to speak up? Jin Woo Kim.
Yes, thank you. I have a question is, it's a very interesting speech. I was very interested a bit because babies, when they train their motions, they use their cerebellum, and usually the method that they use is something very much like what you've described. First, they use a feed-forward planning, and they try to imagine what would happen in the short term, something like your own geometric motion planning. And then they have a storage of how their motions affected the environment, and they build upon that knowledge to execute a new problem. So, for instance, when a baby reaches for something, and first they successfully achieve it, and when they are confronted with a more complex problem, they would build upon that base knowledge and try to navigate through a more complex problem. I was wondering how difficult it is it to scale up from a more simple object? I mean, all of your representations have been 5 or 6 or even 10 objects on the board, but I was wondering if there is any solution by solving a more simpler 2 to 3 problem and then scaling it up slowly. Is it difficult?
So it is difficult, obviously, in the sense that if you have many more objects, then predicting the physics of those many objects interacting with each other becomes even more computationally expensive. And this answer is, I realize that your question is coming from very much a cognitive science and human brain point of view, and my answer is very technical. I'm saying computational expense is but if we wanted to immediately scale the number of objects in our implementations, the immediate effect we would see is that it will get even slower, right? And so it would get difficult. But I think, just to point out where I think the solution is, I think the solution is in developing algorithms that can identify the lower dimensional, even if you have that higher dimensional problem, even if you have many objects, identifying the lower dimensional problem within that higher dimensional problem. Because I don't think even we humans, when we see when we are confronted with that many objects, we are not necessarily predicting how all those objects will be moving, right? We are not necessarily predicting. What we are able to do is to identify through attention and through through our brain, we are able to then reason about the lower dimensional structure of that problem. What are the important dimensions of the problem that I have to solve the problem in, and then solve the problem in those dimensions. And I think this has some connection to my point about the coarse physics models, because you can think of the coarse physics models also in terms of lower dimensional physics models. So, for example, you can think of when you're confronted with a scene of many objects, you can plan, the easiest way to do this would be forget about the other objects, just plan with the physics of the target object and maybe the objects that are most in front of it, okay? And forget about the rest. They will probably not matter. If they matter, you will then add them to your representation and you will gradually increase the dimensionality of your problem, right? So I think that is how one can scale these approaches to and that is something that we want to do. Yeah.
So if I may, it's a connected point, but I was actually thinking about the coarse physics and the fine physics models. And one of the ways that babies or even adult humans react with physical objects is to feel their weight, to estimate how much movement that we've given reacts to something else. Yes. So is implementing just only vision or perhaps some feedback on how we have moved certain objects. When we're drastically overestimating something, we might think it's heavy, but it's suddenly very light.
Yes.
Those reactions actually compute very much into our motions of what we plan. Is there any?
I completely agree with that. And, in what I have shown, there is none of that. We haven't done that, not because it is not important, but I agree, with this kind of interaction, we do need to look into continually estimating the mass of the object, the friction of the surface. We can use all that feedback as we are executing to have better and better models of the environment. I have done some work in the past that I didn't show here, where we do use tactile sensors on the hand as we push objects to estimate some parameters. But we definitely need to do more about that. I agree with that.
Thank you.
Yeah, thank you.
Okay, I think the next one is, I'm going to briefly jump the queue here. So I'm going to jump to a student and then I'll come back to staff. So Saif goes first. After that, we'll go to Iran and then Hector.
Hi.
Hello.
Thank you for your talk. It was very nice. Thank you. I think my question is partially answered in your previous answer, but I just wanted to ask, so when you update your physics simulator using the camera, you have this real feedback and correction of the object positions in the simulator, and you're only doing the correction for the physics, the locations itself, and not any of the physics parameters.
Yes.
Okay.
Yes, that I agree that my previous answer was exactly about that. I agree. I think you're very right in the sense that positions are, you can think of them as parameters of the environment, and there are other parameters of the environment as well, right? The shapes of the objects, the mass of the objects, the friction coefficients, the inertial matrices of the objects. So you can definitely use the information to constantly improve your estimates about these parameters as well.
Sorry, and just another question I had is, so whenever you mention physics model of the environment, do you always mean the simulator, or did you ever use any other learning method to model your physics?
So we did, in that coarse and fine model that I talked about, I mentioned the coarse model as a hand-coded model. If you remember, I showed a prediction where, I won't be able to find it now, but I showed the prediction as moving with the pusher and then slightly rotating.
Yes.
One thing that we did as a follow-up to that has been using learned models as the coarse model. So we did train neural networks within a simulator.
Okay.
So in simulator, we pushed on multiple objects and generated lots of training data. And then we trained a neural network.
Okay.
And so that we can then query the neural network to make physics predictions for us.
Based on the object, is the parameters of the objects part of the model as well?
That's a good question. I think we didn't make mass and other things like that parameters, but we had the shape of the objects as parameters. And again, it wasn't as general as it can be. That's also, again, a good point, in terms of the parameters of the models. But the main idea we wanted to try was, if we can use learned models as the coarse models. And I agree with you that, you can do it in a better way than we did. You can actually make those models even more general and powerful by feeding in also the mass of the objects, or whatever information you have about the objects. But we basically trained in simulation like that, so that later during planning, we can use the predictions of the network as the coarse model together with a simulator again, to use in the same way by combining them through iteration as much as we want, to then predict physics in a faster way.
Yeah, I was just wondering if the reason you did not incorporate the mass into the, or mass or any of the dynamics parameters into the model is because this is more of a question because I'm not sure. So do you think it's possible to capture this just using the real-time feedback from a vision system and just correcting it with position? Do you think it's able to capture that?
Capturing the mass of an object from vision.
Yeah, not the mass itself, like the dynamics response of the object. So do you think just from the feedback? So for example.
Oh, I see. I see what you're saying. So for example, if you just have a visual sequence of how the object moves, can you extract dynamic parameters? Yeah, I mean, of course you can get some information, right? Like, if at least if you know something about the forces that you're applying as well. So, you know, there I'm breaking out of your constraints a little, because, you know, if you really want to assume that you don't know anything about the force you're applying, right? If you're really just constrained to vision, and if the problem is that you're not telling me about anything about the force, then it may not be possible, right? Because, but if I have some information about at least like some limits of the possible forces that I'm applying and some limits on the possible friction of the surface and things like that, then you can get to estimates on the inertial parameters of the object. That's correct. Yeah.
Yeah. Okay. Thank you. Just a final question.
Saif, I'm going to pause you, right? Let me make sure others to get a chance. If there is a chance, I'll come back to you. Okay.
Sure. Sorry. Thanks.
And I can also say why you can have a separate chat with Mehmet later if he has time, because he is doing a sort of follow-up work with dynamics and trying to build models. That's why he's asking these questions. Anyway, so let's go to Iran, please.
Thank you, Mehmet, for his great talk, and it was impressive, your work, your student, and your collaborator. I try to be brief in my question as much as I can. So my question is a bit related to the last part, and also is a follow-up of Aaron's question, but not from the evolution point of view, from the knowledge representation. So you mentioned that, for example, jamming is a problem, but I mean, if we can able to reason about the affordability, meaning that some object actually is jammable. So we kind of, it gives us more solution, and it helps us in reasoning about how we push and, in which direction probably we want to push. And related to knowledge representation again, I saw Tony Khan as one of your collaborators. I assume that you kind of, in your joint collaboration with Tony, you work on the reasoning about, direction and minimizing the gap and et cetera, which my concrete question is, did you explore idea of actually using reasoning about direction and topology in a high level as an input for your initialization of optimization algorithm?
Actually, we did. I mean, and your question is so spot on that it makes me think maybe did you see a paper like that? Because we exactly did
Tony last year on Ichikai.
Okay. Because I didn't talk about that work here, and I agree. Aaron's question was also related to that, and I didn't want to confuse you by going into that, but. Together with Tony and others, we also had a project where we were trying to extract human decision-making in such cluttered scenes, object manipulation scenes. And we collected lots of human manipulation data where in virtual reality. And there's a ICRA paper, I think, 2020 or 2019, I guess 2020. If you're interested, I'm happy to send you the PDF. And then we basically used, this spatial relations between the objects and the gaps between the objects, and there were these concepts of the gaps and objects, and then we would try to understand how humans generated their plans in terms of these objects and the gaps, and then take that and initialize one of our optimizers, exactly what we did, what you said. So we did that, and there is still a postdoc, Mohammed Hassan. He is still improving on that as well. Like, you know, so that work is still ongoing, actually. Yeah, we did that. I didn't talk about it here, mostly because, like, you know, it's a big collaboration, and I focused more on, you know, more or less where I was leading almost all work. So, but so why not take that approach completely? Like, why not go to the semantic space? I think we can go to the semantic space, and there is a lot of interest in robotics right now. You know, with task, there's this thing called task and motion planning, where the task level is usually the symbolic level. And then
in task and motion planning, that's how your question comes from, actually.
Yeah, and I think it is interesting.
There's a bot here. I mean, I sense a bot, but I mean, I don't want to prolong my question and leave the time for the others.
Yeah. But so yeah, we can discuss this. I think.
Thank you.
Yeah. Let me say that I think that question is interesting. I am much more excited by more continuous physics models, not because it is more interesting, I think, but I think this idea of coarser, lower dimensional models also has some potential in them, in addition to even higher level symbolic models. And there's not that many people looking into it. So that is where I'm trying to focus on. That's why I focused on that. Yeah.
We can follow
Mehmet, you're perfectly okay for you to have strong opinions. Nobody's gonna.
Yeah, I mean, I don't. If I had a, like, you know, I would, but, like, you know, yeah, I think starting for, like, you know, those continuous models are.
Yeah, if they are more interesting to you, they are interesting. Yeah. Why not? Yeah, of course. Okay, I'll give Hector a chance, right? And then, because I know we have already maxed out and people will start wanting to drop off. So let me go to Hector. And any other questions? I'm not seeing anything here yet. Oh, Aaron has something. But if there are any, we might leave it to later. But we'll see. Hector, go first.
Okay. Thanks, Mohan. Hi, Mo.
Hello.
Thank you very much for the very fascinating talk. I'm a postdoc in vision here, and I look at things from a different perspective, but I have the same sort of questions and interests. So I look at how you can understand 3D scenes or 3D collections of objects by using physics to make into to predict what might be occluded. So okay. It's quite a different thing, but I have the same sort of questions about representations, fidelity of physics, and also how to deal with uncertainty. And I was curious, it's kind of, I guess, related to Anne's and Aaron's question from the opposite perspective. So I'm interested in your learned heuristic and the reduced trajectory planning, but from the perspective of understanding what is the actual learned heuristic doing under the hood. So I noticed that you're showing it images where you have semantics, which consists of essentially 3 classes. You have the gripper, you have the object of interest, and then everything that's not of interest, or the other objects rather, are the same color. So presumably they're all in part of the same class.
Yeah. And
I was wondering, does the system behave differently if you sort of segment instances? So does it need to know that when you have background objects that they're 2 different objects, or does it behave the same as if you just treat it as a single sort of obstacle? Because presumably if you have 2 background objects that are touching, then if the system doesn't know that they're different objects because they're the same color, then it might treat them as one continuous obstacle. And so the question is it planning based on avoiding obstacles primarily, or is it sort of thinking about how we could potentially in the future move two objects in a way that will help it, to background object potentially? That's the first question.
So you mean moving them to identify whether they're a single object or they're two different objects, to that kind of separate?
I was thinking more about, is it planning based on sort of thinking about what would happen to two separate objects, or is it planning based on sort of obstacle avoidance, I suppose?
No, it is a physics-based plan in that sense. So it is, if the vision system is able to detect them as two separate objects, it will plan based on the fact that they are two separate objects, and it can try to push on them at the same time or separate them and go in between them. So it will be able to do that. But it depends on one thing that we are doing in that work is really relying on that off-the-shelf vision component that we are using, and it's not our contribution, right? So we are relying on it to give us good shapes and good detections of the objects. And in your question, if you have two objects side by
sorry, my question is not really looking at the explicit physics simulation, but looking at the heuristic. So that you have a learned heuristic which tells you how good a future state is. And my question is really, what is that heuristic actually using under the hood to determine how good that state is?
I see.
I mean, because it doesn't have an explicit concept of background objects as individual objects, just as sort of
that's a
obstacles, I guess.
So that heuristic is basically just, we get that image from the simulator, and then we feed into a neural network, right? So and we get the value, in the sense of the value of a state in an MDP. The value of that state is what the neural network predicts, and we just get that value, and then that is our heuristic. And how we train that neural network? Well, we train it in a reinforcement learning fashion. We don't know exactly what the network is doing, obviously, when it predicts the value, but it is predicting according to its previous training interactions with it. But you are right in that if you had two red regions in that image that were touching each other, I think that's a very good point you're making. For the neural network, they may look like the same object, and it may look, it may be fooled by that. So I think that is a very good point. That's possible, definitely.
Okay, thanks. So you haven't looked at what happens if you train it with different colors for each object?
So the colors of the objects, that is the thing. So we always color, we color those objects, right? So when we, let me go there. So, yeah, so can you see this?
Yes.
So if you can see here, so this is the state that we create from this state, and we assign these colors to all these objects, okay? And then we create the simulator, and then these are what goes into the network to predict the value, because these are the leaves, okay, of our search. And we assign these colors to the objects, and why would we assign different colors?
So the idea is that, if my understanding is correct, you're feeding in sort of a 2D image to the heuristic network.
Yes.
And in this 2D image, the pixels for the apple and the orange, I suppose, and the bottle are all the same color.
Yes.
But you could choose to give them different colors, because presumably your vision algorithm is segmenting out individual objects. And if you gave different colors to the pixels for each object, then your heuristic would know from the data directly that they are different, or
I see.
you hope
I see
it
what
would
you're
be
saying.
able
To
to
solve
do it,
that problem.
but
I
they're
see.
different objects.
Okay, I agree with that. I agree with that. That's a good point. I agree with that. That would help the network to distinguish between different objects. Though, like, you know, then the learning problem may be a bit harder because, you know, you are asking the network to learn a more varied representation in terms of the input space, right? So here, everything being read is kind of easier for a network. But no, we haven't tried what you suggested.
I see. So it's quite important. Okay.
Yeah.
I think given that we are gone above the time limit, I think I should wrap this up here. But Aaron, I'm sorry. Is this okay? Because we've gone way over time, and I know people wanted to go elsewhere. So
that's fine.
Yes.
Just give David Hogg my greetings. Yeah, I was his supervisor, but he taught me more than I taught him. I think that was a million years ago at Sussex University.
Okay. Yeah, I will. Thank you.
Okay, so in that case, I'm going to end with, say, applause for our speaker. Thank you.
Thank you very much
for coming and giving this talk. Well, coming electronically and giving this talk. And if anyone has questions, I'm sure Mehmet will be happy to take them through email or like another.
Obviously, right? Yeah, I'm happy to meet as well if you want to have a chat. Yeah, thank you very much.
Okay, so good. Thank you very much, Mehmet. Have fun working on your research problems. We'll stop here for today. Thank you.
Okay, thank you very much. Bye.
Bye.